Okay, I guess we can get started. So, does anyone have any questions about the homework or anything from the past few classes at this point? Okay, then I guess we'll just pick up where we left off. And we'll be talking today about a special extension of a Markov model called a continuous time Markov model. We'll abbreviate a CTMM. And the idea behind a continuous time Markov model is that we're going to continue to assume that we have a model with some finite or at least discrete set of states. So we've got some graph describing states, transitions among them and all of that. But we're now going to assume that there is a real valued time attached to our progress through the model. So instead of assuming that we're in state Q1 at step 1 and Q2 at step 2 and Q3 at step 3 and so forth, we're going to assume that our transitions between states are occurring on a real number line. So maybe at time t0 we start our model, and then maybe we're in state Q1 at this time, and then at some time t1 we move to, say, a state Q2, and then maybe at some other time in the future, T2, we move back to state Q1, and so forth. And the assumption can be that these times can be any real numbers. So we're no longer looking at a discretized version of time, although it's still a discretized state set for this kind of model. And this allows us to simulate or model a much broader class of systems than we can with the pure discrete Markov models. So to understand how that works, we need to generalize some of the definitions we've had from working with general Markov models. And one of the important definitions we're going to need for understanding these is what I'll call Pij of t. So if you remember previously, we saw a definition of a Pij of n, which would be the probability, if we started in state I, that we're in state j after n steps of a discrete model. And this is the analogous thing. It's the probability that our state at a given real value time t is qj, given that our state at real value time 0 was qi. And that's going to be the basic property we'll be paying attention to in this model. Now, it's possible in between going from I to j, it's passed through any arbitrary set of states. We're only defining, given where it starts, what is the probability that at this exact time it's in this exact state, regardless of what you did in between those two things. And that's going to be the key property we'll be keeping track of to analyze these models. So does that make sense to everyone? Okay, so for a continuous time Markov model, we're not going to want just arbitrary distributions for this really family of probability densities. We're going to want a generalization of the normal Markov property, which you sometimes refer to as a Markov model being memoryless. So in a generic Markov model, we say that the model is memoryless or has the Markov property, meaning that what happens next from a Markov model depends only on your current state. The probabilities of movement to any next set of states are independent of the previous states you've been to, only the current one matters. And the analogous version of this for a continuous time Markov model is formally stated as follows. The probability that we're in state j at time t, given that we were in state I at time 0, which we've defined here as the probability q of t equals qj, given q of 0 equals qi. We define to be equal to the probability that q of s plus t is equal to qj, given q of s equals qi for any s greater than 0. So we define that these things are identically equal for any positive s, and that is going to put a lot of limits on the possible probability distributions, but it's also going to ensure that our model has this memoryless property. Essentially, what the model does next is independent of where it's been in the previous steps, as well as independent of how much time has elapsed before we started looking at state I. So does that definition make sense to everyone? Okay, so this in particular is going to put a very specific limit on what the probability distributions of these times can be. And in particular, what we're going to see is that it ends up guaranteeing that the times between these successive steps will always be distributed as exponential random variables with some rate lambda. And we'll see how that works, how you derive that kind of rate lambda. That's the basic limitation on the model. To understand how we get there, there are a couple of ways of thinking about continuous time Markov models that I find useful. And one of them is to think of a continuous time Markov model as kind of a limiting case of a discrete Markov model. And I'll show how that works. So let's say we've got some state Q1 that we're in at a given point in time. And we'll assume this has a set of neighbors, maybe Q2, Q3, Q4, and so forth. And I'm going to define a particular kind of probability on each of these edges here. I'm going to assume that each of the edges has some intrinsic rate, like a rate lambda 1, 2 of movement from state 1 to state 2. And the probability then will be lambda 1, 2 multiplied by some small time delta t. So that's going to be the definition of the transition probability from state 1 to state 2. And similarly, from 1 to 3, we're going to have a lambda 1, 3 delta t. And to 4, we'll have a lambda 1, 4 delta t. And that's going to imply that we also have a self-transition probability, which will be equal to 1 minus the sum over j of lambda 1j delta t, where the j's are summing over all the neighbors of state 1. So in the limit as delta t goes to 0, these probabilities of moving will become infinitesimally small. The probability of staying where you are approaches 1. But we can turn this into a meaningful continuous model by thinking about this in terms of that limit as delta t goes to 0, but also as the time between steps goes to 0. So imagine we take this discrete model and we just say that we'll take a step every delta t. So we're running the discrete model, the probabilities as I defined them, and every time we take a step in the discrete model, we accumulate delta t worth of time. If we then take the limit, then your probability of moving on each step is approaching 0, and the limit as delta t goes to 0. But the amount of time you need to make that step is also approaching 0. So you come to a kind of limit in which the amount of time you need per step is getting small, and the probability of moving in the step is getting small. And so you will come towards kind of approaching a constant average time per step. And in particular, what's going to happen is that, let's say we look at this particular probability here. What is the probability distribution of times we spend, let's say number of steps we spend in state Q1 before we move? What kind of probability distribution would that be? We can think of it like flipping a biased coin, and the limit as delta t goes to 0. This is a coin that almost always comes up heads, but every time it comes up tails, that means you're moving in one of these other directions. So what kind of probability density does that describe? Well, not quite a binomial. So a binomial would be effectively, if we were adding up a set of these, we'd get binomial.
I said Bernoulli.
Oh, Bernoulli.
Yeah.
So Bernoulli, well, each step we would be using a Bernoulli variable, but the number of steps is related to the Bernoulli. Does anyone else have a guess?
Geometric?
Yeah, it's going to be a geometric random variable. So the number of Bernoulli trials you need to get a successful trial is distributed according to a geometric random variable. And geometric random variable means that we'll have something that kind of looks like this, or a probability of still being in state 1 after k steps will decay something like this. And what we're going to be assuming then is that the amount of time we spend in that state is going to be the number of bars we need before we get a success times delta t. And essentially what's going to happen as we make these bars thinner and thinner, but make the probability per bar smaller, or closer and closer to 1, is that this will converge on a smooth continuous distribution. And in particular, it's going to converge on an exponential random variable. So basically, that's kind of the limit of a geometric as you move towards infinitely small probability of moving, and infinitely small steps for movement is the exponential. So that's one way of deriving what a continuous time Markov model is. So taking this discrete model and the limit as delta t gets very small. And you could get a reasonable simulation of a model like this by just running it for some finite but very small delta t. The recognition that the limit is exponential, though, lets us come up with a different view that's much more practical for simulating this kind of model. And that view works as follows. Let's say we're in state 1, and we're considering all these other moves to state 2, state 3, etc. Then an equivalent thing to this model I'm telling you about here turns out to be the following. We will define an exponential random variable with a rate lambda 1, 2. We'll define an exponential with rate lambda 1, 3 and rate lambda 1, 4. And what we're going to say is, we'll imagine that each of these edges has a timer on it, and the amount of time it's counting down is a random variable distributed according to these exponentials. And the first of these timers that goes off, we move in that direction. So if this is the first one that goes off, we move there, and the time we move is the time that timer goes off. It's not obvious that that's equivalent to the limit here, but those actually are equivalent. And that gives us a very simple pseudocode for simulating a continuous Markov model that works as follows. We'll start with some time t equals 0. We'll start with some initial state. Let's call that q0. So qi is our current state. We're starting at q0. And then to simulate the continuous time Markov model, we just repeat the following steps over and over. We'll pick some t minimum, which will initially be infinity, and then for each edge I comma j, so each neighbor j of state I in the graph, what we're going to do is the following. We'll say the timer for that particular edge gets an exponential random variable with the appropriate rate, so lambda ij. If that timer Tij is less than Tmin, so this is the shortest time we've seen so far, then what we're going to say is Tmin gets Tij, and we'll call this Qnext gets Qj. And then what we do is run through this for each of these neighbors, so n the if and the 4 here, or excuse me, yeah, n the 4. And then we'll say whatever one of these turned up as the smallest, that will become our next state, so qi gets qnext, and finally t gets t plus tmin. So that's exactly what I was describing here. Pick an exponential random variable from the appropriate edge distributions, and then whichever of those is the smallest, you move in that direction at the time equivalent to the value of the smallest of these. Is that algorithm clear to everyone? Okay, so that is basically the simplest way of simulating the continuous time Markov model.
Yeah, in the discrete case, we had probabilities on the edges where the probabilities added to 1. In the continuous case, what exactly are the numbers for the edges? And do they have any constraints, like they have to add something?
Well, the numbers are, we would think of them as rates, so rates of movement in different directions. So they have to be positive. They don't have to add to anything. So in a sense, whatever positive number you come up with here in the limit, they'll go to 0, so you can still evaluate this thing, which will really be the self-transition probability. We will see later when we get to analysis of them, there's kind of an equivalent of a self-transition probability for these that we simply define to be minus the sum of the lambda j's. So basically, you kind of have a virtual negative self-transition probability, which I know it doesn't make sense, but turns out to be the thing you need for the math to work out. But basically, as long as the rates are positive, it works. Any other questions?
What's the case where you would rather use a continuous time Markov model rather than a discrete time model?
Yeah, so there are a number of examples. We'll actually see a few of them in subsequent lectures. I'll give some examples in this lecture, but well, one example we'll encounter later in the class, actually in the next lecture, is that these end up being important to a kind of model that's frequently used in population genetics for simulating evolution of populations. So basically looking at, in relatively large populations, times between events, where events usually mean two people having been descended from a common ancestor. They're also very important in models of reaction networks. So very often, if you're thinking about what's called a well-mixed reaction system, so lots of things kind of randomly diffusing, you can approximate times between reactions by exponential random variables, and then the progress of the system becomes described by one of these models. And those are used quite often in models of small-scale reactions, as well as in similar applications in structural biology. So those would be a couple of examples we'll be seeing later. Any other questions? Okay, well, that basically gives us the tools we would need to understand what a continuous time Markov model is, and we can then start doing some analysis to try to figure out properties of these models. So one property we often care about is what is called the waiting time distribution. And the waiting time distribution is simply the question of, if we're in any given state, how long do we wait before we leave and move to some other state? And that's something we can analyze by knowing these versions of the Markov model, or the continuous time Markov model I've just told you about, and in particular, knowing the representation of it in terms of exponential timers. So in particular, if we have a continuous time Markov model, and I'll just say generically, let's say we're in the state Qi, and then we've got various other states, Q1, Q2, up through some Qk that are our neighbors, and we'll assume we've got rates, let's call them lambda 1, lambda 2, through lambda k. What we're interested in is, what is the time to leave state Qi? Because these are memoryless, it doesn't really matter when we start watching state Qi. So at any point, if you look at it and you see it's in state Qi, and you ask, how long do you wait before it's in some other state? That would be a waiting time. And we can pose that in terms of these exponential random variables, the x lambda 1, lambda 2, lambda k, and so forth, by saying that the waiting time distribution is simply the minimum of a set of independent exponentials. So it's the minimum of an exponential for each of the edges that we're considering. And that follows directly from this algorithm here. We're just running through a set of independent exponentials, picking the minimum, so that's going to be our waiting time. And that ends up having some very nice properties because of the, well, really they're nice properties of the exponential random variable that follow through the continuous time Markov models. And we can see that by working through some math to see what this definition really means. So if the distribution of this is the minimum of these exponentials, or the time, the random variable that describes the waiting time, then that random variable is going to have a distribution function that is the probability, the minimum of these x lambda 1 through lambda k random variables is greater than some t. That's the definition of the probability distribution function for this random variable. And since these are independent random variables, that is going to be equivalent to the probability that the first one is greater than t, and the second one is greater than t, and so forth, and up through the kth one. So in other words, the probability that the minimum is at least t is the probability that the probabilities of each of these being at least t. So the probability the x1 is at least t times probability x with lambda 2 is at least t, etc. Now, exponential random variables, we've seen the probability distribution function for these before. It's simply e to the minus lambda t. So this one, the probability distribution function, probability x lambda 1 is at least t, is simply e to the minus lambda 1t. And the next one is e to the minus lambda 2t, etc., e to the minus lambda k t. And we can simplify that by saying that that is simply e to the minus lambda 1 plus lambda 2, etc., up through lambda k t. And then if we kind of reverse the logic we were using to get here, we can say that this is simply equal to the probability that an x lambda 1 plus lambda 2, etc., up through lambda k random variable is at least t. So I'm just saying that this is the density function for that particular exponential random variable. And what that's telling us is that the waiting time distribution is described by this random variable. So the waiting times are exponential random variables where the rate is simply the sum of the rates of all of the possible ways of exiting the current state. So that tells us some basic properties. So an exponential random variable, for example, has a mean value that's equal to 1 over its rate. So we can say the average waiting time is simply 1 over lambda 1 plus lambda 2, etc., through lambda k. So is everyone with me so far? All right, so that is one property we can derive that follows through from the fact that exponential random variables in general have these nice properties of, in this case in particular, the property that the minimum of a set of independent exponential random variables is itself an exponential random variable, and that's basically the key to that property. Another property we would often care about is if we are in our state qi here, what is the probability of going to any of the other neighboring states? So what is the distribution of next states that we would consider from that kind of model? And a way of posing that is, if we've got a set of given states, what is the probability the next state is, let's call it qj, given current state is qi. That's another thing we can derive with some basic probability transformations. So in particular, we can pose this by saying the probability the next state is some particular qj out of all of the possible neighbors, and let's assume again we have k possible neighbors, is equivalent to saying what is the probability that an exponential lambda j random variable is smaller than all of the others. So smaller than the minimum of the exponential lambda 1 and exponential lambda 2, etc. All of the ones except this, or equivalently, the probability the x lambda j random variable is less than the minimum over j prime not equal to j of a set of independent x lambda j prime random variables. Okay, so if we want to figure out what that is, does anyone know how we would pose that? One of the first things we want to do is maybe simplify this term. So can anyone figure out a way to simplify this?
1 over 1.
Yes, that would give us the mean value of this, but in general, we have a set of independent exponential random variables, and we just figured out that the minimum of a set of independent exponentials is itself an exponential random variable. So this thing we know will be distributed as an exponential random variable, and in particular it will be distributed as an exponential whose rate is the sum of all of the rates of the outgoing edges except for the j edge. So we can figure out what this sum is, add up all the values except for j, and I'm going to refer to this as lambda star, the sum of everything except all of the outgoing edge rates except for this particular one, lambda j. So we're now asking, essentially, what is the probability an exponential of rate lambda j is smaller than an exponential of rate lambda star? So that's what we're trying to ask here. Probability x lambda j less than x lambda star. And we can apply some basic tools from probability to figure out what that is. In general, the way you would pose the problem of figuring out if one random variable, let's say x, is smaller than another random variable y, is you do a double integral over the ranges of these possible values, summing up the joint density of those over all the pairs of values for which the thing you're testing is true. So in other words, what we want to do is say, we'll do an integral over x and an integral over y, and we'll look at all the possible values of x, 0 to infinity, but we'll just look at the values of y where this is true. So in other words, we're integrating y from x to infinity, because if y is at least x, then this assertion is true. And we want to do that double integral over the joint density of these two random variables, which is going to be, since they're independent random variables, simply the product of their individual densities. So we're going to have a lambda star e to the minus lambda star y, and we're going to have a lambda j e to the minus lambda j x, and then we're simply integrating that over y and x. So that is equivalent to this probability. Does that make sense to everyone? Okay, so we can then go through and evaluate what this is. So I'm first going to take this piece that only has the y in it. We can move this kind of beyond the dy because there's no y there, and evaluate just that inner integral, integral x to infinity lambda star e to the minus lambda star y dy. This is just integrating an exponential, so the value of this is going to come out to minus e to the minus lambda star y, evaluated at x and infinity. At infinity, this goes to 0, and then the other limit is going to make this thing equal to e to the minus lambda star x. And we can then plug that back in for this piece here, and we've converted this to a single integral from 0 to infinity of e to the minus lambda star x times, we've got this lambda j, e to the minus lambda j x dx. We can combine the exponentials here, get integral 0 to infinity, e to the minus lambda star plus lambda j x, leading lambda j here, dx. And again, what we're doing is just integrating a simple exponential. So you just divide by the rate of the exponential, and what we end up with is lambda j over lambda star plus lambda j, another leading minus here, e to the minus lambda star plus lambda j, x evaluated at 0 and infinity. At infinity, that goes to 0. At 0, this piece, the exponential, becomes 1, and we put it all together, and we get the probability is lambda j over lambda j plus lambda star. And we can note that since lambda star is just the sum over all of the rates except j, what this is telling us is that the probability we move in the direction j is simply proportional to the rate of j. Your probability of going in any direction is proportional to the rate of that transition. Does that make sense to everyone? Okay, so those are some basic properties. I think it's useful to know how they're proved, but for the most part, it's worth just knowing them independently of how we prove them, because they'll help us quite a bit in analyzing these models as we use them more often. So to see how we can use these, let's take a simple example. Let's suppose we've got a continuous time Markov model that looks like the following. We'll imagine that we are studying a system with protein folding. So maybe we've got a protein and it's got two domains in it. And we're going to assume that it can fold in two ways. So we've got a domain 1 and a domain 2, and it's possible that domain 1 folds and domain 2 is unfolded. Or it's possible that the first thing that happens is that domain 1 is unfolded, but domain 2 folds. And we'll assume that those can happen with some rates, let's say lambda 1 and lambda 2. And then either way, whichever domain didn't fold, we're going to assume then proceeds to fold. So we get our final folded protein. And we'll assume that that happens with rates lambda 1 for this direction or lambda 2 for this direction. So that would be our continuous time Markov model. In this case, it's not an ergodic model, so I'm assuming it's unidirectional, that you go here and then you're committed, and then at that point you go to the next step. But we can analyze some basic properties of this using the things we've already shown about the exponentials and about continuous time Markov models. So is the model clear for everyone? Okay, so one thing we might be interested in is, let's call this pathway 1, and let's call this pathway 2. So there are two possible pathways. We can ask, what is the probability we take pathway 1? So we fold domain 1 first, then domain 2. Can anyone figure out how we would evaluate that?
First we take probability of going to the state where the first one is folded.
Yeah.
From the earlier calculated.
Yeah, so because we're assuming the edges are unidirectional, basically the first move commits you to take one pathway or the other. So we're just asking from the starting state, how likely are we to go in this direction versus this direction? And we already figured out that that's proportional to the rates. So the probability we take pathway 1 would be lambda 1 over lambda 1 plus lambda 2. And then that tells us that the probability we take pathway 2 is 1 minus that, which would be lambda 2 over lambda 1 plus lambda 2. So everyone follow that? Okay, so a trickier question would be, what is the mean time to fold the protein? So given that there are two possible ways of folding it, how much time on average does it take to fold? So that's a question we can pose by first of all noting that folding is always going to be a two-step reaction in this process, although there are two possible pathways. And we can break this down into the expected time to fold is equal to the expected time for step 1 of folding plus the expected time for step 2 of folding. These may not be independent random variables. So if one step, let's say this one, has a much higher rate than the other, then knowing that it folded the first step very rapidly might tell you that you're more likely to be on pathway 1. But it turns out that that doesn't matter because expectation is always linear. So it doesn't actually matter that these random variables depend on each other. So what is the expected time for step 1?
The average of lambda 1, lambda 2, or 1, yeah.
Well, not quite the average. So what is the expected, what is the probability distribution of waiting times to get out of the initial state? Well, there are two ways to get out that have rates lambda 1 and lambda 2. So the waiting time is described by an exponential random variable whose rate is lambda 1 plus lambda 2. So you add the rates, and the expectation of an exponential is 1 over its rate. So the expected value of the first step is 1 over 1 plus lambda 1, or 1 over lambda 1 plus lambda 2. The expected value for step 2 is a little trickier. We need to use some conditional probability to consider the fact that it will depend on which of the pathways we took, but we can basically say that it's going to be the expected time for this step multiplied by the probability we took pathway 1. So the expected time for that step is 1 over lambda 2 times the probability we took pathway 1, which we figured out here, lambda 1 over lambda 1 plus lambda 2. And if we don't do that, then the expected time of the second step is 1 over lambda 1, and that occurs with probability lambda 2 over lambda 1 plus lambda 2. And we can simplify this a little and evaluates to lambda 1, lambda 2 plus lambda 1 squared plus lambda 2 squared over lambda 1, lambda 2, lambda 1 plus lambda 2. So that then would be the expected time to fold the protein. So does that make sense to everyone? Okay. And so that gives us some simple examples that we can explore using these basic properties of continuous time Markov models. But there's some more sophisticated tools we can use if we really want to understand in detail how these behave over long time scales. In particular, there's some basic mathematics known as the Kolmogorov equations. That allow us to analyze in great detail the time evolution of a continuous time Markov model. And to use that, we have to take the definition I had mentioned briefly earlier, that we will define for our model a set of self-transitions where any state will have a self-transition rate lambda I, which will be minus the sum for j not equal to I of lambda ij. So we're just defining these negative self-transition rates. And then what we're going to do is use this to analyze the probabilities Pij of t as we saw before. So the probability we're in state j at time t, given that we're in state I at time 0. And there are two versions of the Kolmogorov equations. The ones we'll use most often are called the forward Kolmogorov equations, and those are stated as follows. They say that the derivative of Pij of t with respect to t is given by the sum, or let's call this k equals 1 to n of Pik of t lambda kj. So this is sort of like, if you remember, the Chapman-Kolmogorov equations we mentioned very briefly back in discussing discrete Markov models. Intuitively, what this is saying is that the rate of movement into state j from at time t from a starting point of state I, we can derive by summing over the probability we've ended up in any intermediate state k times the rate of movement from k to j. So it's just summing up over all of the possible places we might have been instantaneously before going to j. And that gives us a way of describing the time evolution of these as systems of differential equations. This particular set of equations we'll sometimes see referred to by some other names. So in the chemical modeling literature, you'll often see this referred to as a master equation, and physicists tend to call these Fokker-Planck equations. But basically, they're ways of understanding the time evolution of this kind of system. There's also a set of backward Kolmogorov equations. And they're more or less the same thing. They're saying that the Pij of t dt is equal to some k equals 1 to n of lambda ik pkj of t. So So you'll get a different set of equations, but they, if you evaluate them, they'll lead to the same probability distributions as the forward ones. All right, so any questions about this yet? equal to lambda f over lambda f plus lambda r. Okay, so any questions about that? Okay, so we can then plug in and we can say P00 of t is equal to lambda f over lambda f plus lambda r e to the minus lambda f plus lambda r times t plus lambda r over lambda f plus lambda r. Now we could go through that again to derive P01 of t, but since we know that P00 of t is 1 minus P01 of t, we can just say that 1 minus this must be P01 of t, and if we follow through the math, what that's going to come out to is lambda f over lambda f plus lambda r, 1 minus e to the minus lambda f plus lambda r t. Okay, so that gives us a pair of equations we can evaluate to try to figure out some basic properties of this isomerization system. So what is the stationary distribution of this? What will it go to if you let it equilibrate? What's the stationary probability of state 0?
2 lambda r, 1 lambda, 2 lambda r.
Well, we can figure it out basically by noting that we're asking the limit as t goes to infinity, so this term will go away, and what we'll get is P00 of t, and the limit as t goes to infinity is just this thing, so lambda r over lambda f plus lambda r, and then the limit of P01 would be 1 minus that, but we can see as this goes to 0, this whole thing becomes 1, so you just get lambda f over lambda f plus lambda r. So that's going to be the limit of this system as it equilibrates. But by looking at it in terms of the continuous time Markov models, we get more information about the dynamics of the system. So in particular, we don't just know the stationary distribution, we know how quickly it approaches the stationary distribution. And in particular, the key guiding parameter to understand that is this term here. We know that it approaches the stationary distribution via this exponential decay process with a rate of lambda f plus lambda r. So lambda f plus lambda r is effectively the time scale of the reaction. It tells us how quickly it's going to equilibrate. So are there any questions about any of that? Okay, so I want to walk through then how we would solve this in the more general case, because the tricks we used here only work really because we can reduce it to a single variable. In the more general case, what we would want to do, as I mentioned, is use the eigen decomposition, so use eigenvalue analysis. So if I restate the formula we were working with, we were trying to figure out ddt of P00t, P01 of t. That was given by lambda, which is minus lambda f, lambda r, lambda f, minus lambda r, times P00 of t, P01 of t, and that then is dp dt equals lambda t. So that's the equation we're trying to solve. And if we want to study this in the general case, what we would want to know is the eigen decomposition of this matrix. So what are the eigenvalues and the eigenvectors of lambda? So does anyone remember how in general we would figure that out? Well, I mentioned that one technique you can use to do that is let's say we're trying to find an eigenvalue v. What you would do is take your matrix, let's say lambda, minus v times I, take the determinant of that, that will be a polynomial in v, and then the roots of that polynomial will be your eigenvalues. And once you know your eigenvalues, you can set up linear systems that will solve for the eigenvectors. So in this case, that's complicated enough. I'm not going to walk through all the details of that. I'll just tell you what answers we get out of this. So we're going to end up with that one of our eigenvectors is actually something we can figure out pretty easily from our analysis here. And that is that there has to be an eigenvector that corresponds to the stationary distribution. So we already figured out that the stationary distribution was lambda r over lambda f plus lambda r and lambda f over lambda f plus lambda r. We don't need the scaling constants there. So we can just say that effectively we know that one of our eigenvectors is going to be lambda r, lambda f. And we could verify that, so we can multiply through by this matrix here. We can say minus lambda f lambda r over lambda f minus lambda r times lambda r lambda f is equal to, well, minus lambda f lambda r. So minus lambda f lambda r plus lambda f lambda r over lambda f lambda r minus lambda f lambda r, or in other words, 0, 0. So what's the eigenvalue corresponding to this eigenvector? Well, in general, our assertion would be if x1 is an eigenvector, then our matrix times x1 is the eigenvalue times x1. So what's v? And v is 0. And that's not a coincidence here. In these models, it will always be the case that there will be an eigenvector that corresponds to the stationary distribution, and its eigenvalue will always be 0. So that's equivalent to saying that when you're in the stationary state, then continuing to apply the model is not going to change the probabilities. So the rate of change in the probabilities from the stationary vector is 0. So you'll always end up with that. The other eigenvalue, or excuse me, the other eigenvector is going to come out to the following, 1 minus 1. And we can also verify that that is an eigenvector. So we can say minus lambda f, lambda r, lambda f, minus lambda r, 1 minus 1 is equal to minus lambda f minus lambda r over lambda f plus lambda r. So what is the eigenvalue corresponding to this? Well, this we can observe is equal to minus lambda f plus lambda r, 1 minus 1. So minus lambda f plus lambda r is the eigenvalue. And that also is something we could have figured out from what we had here. So one of the eigenvalues has to be minus lambda f plus lambda r, because that's the rate of decay of one part of this, and the other one has to be 0, because we've got a term that isn't decaying. It has to have an e to the 0t term. All right, so that gives us the eigendecomposition here. So we now know the eigenvalues and the eigenvectors. Did that make sense to everyone? And you understand how to get to this point? Okay, so if we then wanted to derive a set of formulas like this, what we would then need to do is figure out how to get from our initial conditions, whatever we want to declare those to be, to a decomposition of the initial conditions in terms of the eigenvalues and eigenvectors. So we have to declare some initial conditions. And since we've been talking about the model in terms of starting in state 0, that would be equivalent to saying our initial conditions are the vector 1, 0. So what we then would need to do is figure out how to explain 1, 0 as the sum of our eigenvectors, lambda r, lambda f, and 1 minus 1. So we're asserting that 1, 0 is equal to C1 times lambda r, lambda C2 times 1 minus 1. And we want to figure out what C1 and C2 are. So how would we do that? Well, basically, it's just solving a linear system. We've got 2 rows of each of these vectors here. One row, the top entries correspond to the assertion that C1 lambda r plus C2 is equal to 1, and the bottom row corresponds to C1 lambda f minus C2 is equal to 0. And we then want to solve for C1 and C2. So we do some simple transformations here. We can say C1 lambda f is equal to C2. So that's coming from this equation here. We can then plug this back in here to get C1 lambda r plus C1 lambda f is equal to 1. Solve for C1, 1 over lambda r plus lambda f. And then use this to solve for C2, which equals lambda f over lambda r plus lambda f. And we can then say that plugging these back in will give us our decomposition of p of 0. So that is going to be 1 over lambda r plus lambda f, lambda r lambda f, plus lambda f over lambda r plus lambda f, 1 minus 1. And that then tells us what the solution to the general time evolution is. We just use the same decomposition, and we say from that initial condition, p of t is equal to 1 over lambda r plus lambda f, lambda r lambda f, times e to the eigenvalue that corresponded to this. What was that eigenvalue? Yeah, that one is 0, so we got e to the 0t, which is just 1. And then we take this one, lambda f over lambda r plus lambda f, times 1 minus 1, times an e to the eigenvalue corresponding to that, which was minus lambda r plus lambda f times t. If we break that down into 2 equations, what we're going to end up with is P00 of t is what we get from the upper entries, lambda r over lambda r plus lambda f, plus lambda f over lambda r plus lambda f, e to the minus lambda r plus lambda f t, and P01 of t is what we get from the lower entries, lambda f over lambda r plus lambda f, minus lambda f over lambda r plus lambda f, e to the minus lambda r plus lambda f t. And we can verify that this is the same set of answers we got before. So in the general case, if you want to solve a harder system, this is really what you'd have to work through to do that. So you do the eigen decomposition. You find your coefficients to correspond to your initial conditions, and then that gives you the general time evolution of the system. So are there any questions about any of that? Okay, so that's basically everything I wanted to cover about continuous time Markov models. I do have your homework 2s and solutions to hand out. So I think we'll stop here. I can hand those back.